Ciao, Physics 2. All right. Part 1, Wednesday's lecture. Maybe this will be the only part. We'll see. All right, so we're continuing on with the supplemental 3 section on electromagnetic radiation waves. And now we're going to talk about thin film reflection. Thin film interference, otherwise known as looking at bubbles. Bubbles are actually still studied. They're very, very interesting in terms of their properties and the way that they reflect light. The first thing that I ever used an interferometer to look at the densities of was actually soap bubbles. So this is, again, still an area of research, which is pretty cool. Not what we were talking about, but just bubbles in general. All right, so, and also they're so pretty. So there are some interesting optics. And how light reflects off of a bubble. So, and as you know, bubbles are thin and transparent. If you don't remember, go buy some bubble solution, go sit outside, blow bubbles. It is surprisingly stress reducing. It's quite fun. And I mean, I've taken advantage of the fact that I have a child to buy bubble guns, and they're just as awesome as you think they'll be. All right, so the thickness of the bubble drives the interference. And they don't necessarily have uniform thickness all throughout, so they can be a little denser at the bottom, a little thinner at the top. The soap can move around. So let's say a ray of single frequency light, so a laser, hits a bubble head on. In other words, perpendicular. This bubble has a thickness of lambda over 2 for that wavelength. So this is pretty thin, but nowhere near as thin as atoms. We're still off by a couple magnitudes. So let's say, just to get an idea of how many atoms thick this bubble is, so let's say lambda is equal to 500 nanometers. So that would be greenish light. 550 is the typical green laser light, so this would be, I think, greenish. Then it would have the atomic layers of 2,500. So there'd be 2,500 atoms. This bubble would be 2,500 atoms thick. You should prove this to yourself. It's easy. Okay. And to look at interference, we're going to get pairs of atoms together. And consider the path difference. These wordier lectures remind me of being in school, because I still went to school in the days of the overhead projector, where the professor or teacher would sit at the front and just write the entire time. Kind of like what I've been doing now, but in a psychology lecture, it would be just concepts, words, sentences. It was a surprisingly effective way to learn. Maybe you've had a class like that with somebody here who's still using that method. All right, so we're going to pair. Let's pair. Oh my goodness. Layer 1 with n over 2 plus 1. So we're going to go halfway into the bubble, which is equal to layer 1251. And we're going to pair layer 2 with n over 2 plus 2, which is equal to 1252, and so on. So basically, we're going to kind of pair each layer of the top atoms with the corresponding, basically the outermost layer pairs with the middlemost, and so on and so forth until each one of them has a pair. So until n equals 1250 is paired with 2500. Okay, so once again, we're looking at a picture similar to what we saw last time. So we've got lambda over 2. This is layer n over 2 plus 1. And we've got our light coming in from here and our light striking the top layer. So this would be lambda over 4, lambda over 4. All right, so the path difference, because these interference patterns are all about path differences, is lambda over 4 plus lambda over 4, which is lambda over 2. And this will be the case for each pair. So remember, this is a lambda over 2 thickness for the entire bubble. So this is the entire bubble thickness right here, and this is looking at the interference between the topmost layer and the middlemost layer. And then we're going to see this pattern repeated for all the subsequent layers. All right, so this will be the case for each pair. And you'll never look at soap bubbles the same. Therefore, each pair produces 0 intensity. So re-radiated intensity is 0. So we're dealing with a completely transparent bubble, to green in this case, or 500 nanometer light. So, and then of course I'll note, so if the bubble has a thickness halfway between then there's a maxima. Re-radiation. But that analysis is a little bit beyond what we can, what we're doing in this chapter in this class. Okay, so continuing on with bubbles. For a given bubble thickness, you might have the right thickness to get right constructive interference. And this is what gives you the rainbow effect. Because obviously when you're outside, you're getting all wavelengths of light shown at your bubbles. So if your bubble has just the right thickness for the different light or wavelengths of light coming at it, you'll see those gorgeous rainbows coming off them. That's all just constructive interference. Okay. Now, so that we can do a more thorough analysis, let's add the index of refraction. Into our bubble discussion. So we already know that index of refraction is related to how light travels through a medium. And impacts the radiative wavelength. And let's go ahead and look at that with an example. So, we know that a lambda over 2 thickness gives complete destructive interference. Because then you get that lambda over 2 path length difference. So this, of course, for a given lambda. It's not going to be the same if you shine a different wavelength of light on it. So we need to know lambda when it reaches the bubble. And we're going to need lambda prime, which is equal to lambda over n, where n is the index of refraction. Okay, so let's say we have a bubble that is 200 nanometers thick. So we know the thickness of the bubble, and we know the index of refraction. The index of refraction is 1.6. So what we don't know is what lambda of light causes complete destructive interference. All right, so I'm going to call the thickness eta. So we have 200 nanometers. If n equals 1, then lambda equals 400 nanometers. And that would imply that lambda prime is also equal to 400 nanometers. But we know that the index of refraction, let me change that to an if, not an n. The index of refraction is not 1. So lambda is the incoming wavelength. And lambda prime is equal to lambda over n. And so for this bubble, our lambda is going to be equal to 2 times 200 times 10 to the minus 9 meters times 1.6. And so our lambda is equal to 6.4 times 10 to the minus 9 meters, or 640 nanometers. So there's the complete analysis, also taking into account the index of refraction of the bubble and its relationship to re-radiation. All right, so moving on to a diffraction grating. And most of you have all seen laser discs, I think. So CDs, DVDs, and they're both, you can look at them at some angles and you can see your face, and they're mirror-like, and if you look at it at a different angle, you see a rainbow. So think CDs, both mirror-like, you can see your face, and rainbow-like. You can see holographic rainbows. They are hollow. All right, so, and you can see this depending on the angle. So this depends on the angle you're looking at them. One angle, you see your beautiful smiling face. The other angle, you see a beautiful rainbow. I mean, it's kind of a win-win when you look at a CD. And this is all related to an interference effect. So interference effect. So if you take a close look at a CD, and you will see a bunch of little ridges. Radiating out as rings. I think last time I gave this lecture, so normally I would demo this and I'd show it. It actually took me a little bit to find a laser disc. Move beyond them, but you'll see these little rings if you've ever looked at one very closely. So if you've got one lying around your house, take a look. I recommend doing this demo on your own. Also, then you can just kind of take your time with it. And it's sometimes just cool to see that something you've already noticed has some practical implications. Okay, so the distance between the rings is going to be proportional to a lambda of visible light. Otherwise, we wouldn't be able to see this. So you could have a diffraction, so a CD is a diffraction grating. You could have a diffraction grating that would have ridges that were not proportional to visible light. You would get this impact in either UV or X-ray or IR, but you wouldn't be able to see it. So our eyes are incredible photon detectors, but only within a very narrow region. Okay. So otherwise you would not see it. So one of the cool things about chapters like this, and also in teaching astronomy, is that I love making students aware of how much we don't perceive. That the universe is so much more active. We know it's active, but when you realize the amount of events going on in wavelengths of light that we can't even see with our own eyes, but we can detect them, it's really just incredible to think about. Just that level of precision is really awe-inspiring. Okay, so moving on. Awe-inspiring tangent over. So, and these ridges, this causes diffraction. Which then causes the waves to interfere with each other. So, and this is basically how a diffraction grating works, although typically when we use a diffraction grating within a lab setting, you're dealing with something that is rectangular, and you'll have a surface with all of these parallel scratches. They really are quite pretty to look at. And there's all kinds of applications in laser labs. Scratches. Okay, and what you'll see in them is you get both reflection and rainbows. And we've already seen how the angle of light impacts things. And then there's also transmission diffraction gratings. So you would shine a light at them, and then you would see light on the other side, and this is basically, this is like the double slit on steroids. So there's all kinds of applications for these types of, both of these types of diffraction gratings. Not just laser discs. So we use diffraction gratings to measure wavelengths, and therefore frequencies of light. But what I know you're all wondering is, why do we see a rainbow? And so that is, it is the angle at which light is shown that you see, that you get, that you see that lambda. That gives you a particular lambda. So when you look dead on, or perpendicular, all the wavelengths are the same length. So you have equal path lengths. And so to analyze a diffraction grating when you're not head-on, we're going to do a simple example. So let's look at a transmission grating. So we have near infrared light in the form of a laser, so 800 nanometer light. And we shoot it at a diffraction grating nearly perpendicular. So all right, so we're shooting at it nearly perpendicular. And now we're going to talk about what's going to happen at different thetas. There is going to be a peak at theta equals 0, but there can be additional peaks elsewhere. And this is anywhere where the path difference between the slits is 1 lambda. So we're looking for path differences between the slits on the order of 1 lambda. Okay, so let's calculate the angle theta for our light. And for this, we need the d of our grating. So this is the distance between the slits. Our grating has, and you will get this if you look at a diffraction grating, they will tell you this information. So it's going to have 100 slits per millimeter. So our d is equal to 1 times 10 to the minus 6 meters. And we know maximums occur at d sine theta is equal to lambda. So theta is equal to arc sine lambda over 2, which is equal to arc sine. Again, I cannot recommend writing out arc sine instead of sine to the minus 1 enough in your notes. I will be forever thankful to Dr. Elvis for getting me into that habit. And even when I took classes where they just wrote sine to the minus 1, I continued to do that. And boy, were my notes so much clearer. 1 times 10 to the minus 6 meters. All right, so there we've just plugged in. Oh, sorry, that was lambda over d. So we've plugged in our d here, we've plugged in the wavelength of light here, and therefore theta is equal to 53.1 degrees for this wavelength of light. So we would obviously at theta equals 0, we'd see something, but then we would see another constructive interference at 53.1 degrees. So what about, and again, make sure your calculator is in degrees, not radians. What if we shone violet light at the diffraction grating so this could be a lambda is equal to 400 nanometers. All right, so once again, theta is equal to arc sine lambda over d is equal to 400 times 10 to the minus 9 over 1 times 10 to the minus 6 meters. Meters, that was of course an arc sine. And so in this case, theta is equal to 23.6 degrees. All right, so what do we see? The smaller angles are going to give you constructive interference at the shorter wavelengths, so blue, violet, think RGB. And then the larger angles are going to give you constructive interference at the longer wavelengths, so red, orange, yellow, etc. So this is what you will see when you look at a laser disc and you start to angle it ever so slightly. So you will see purple first, and then you'll basically get the rainbow backwards. All right, so let's do an example. We have a diffraction grating with D is equal to 2.3 times 10 to the minus 3 millimeters. A source of single wavelength light has a high intensity beam at theta is equal to 54 degrees to the normal. By the way, these could all be measurements you could make in a laser lab. It all depends on your setup. You measure what's easiest to measure. And sometimes you're changing your wavelength of light as you're going through different optics. And so sometimes you need to verify that things are working the way that you think they are. So these are not just contrived examples. These are real things that you might actually do if you're working in laser physics. So I always enjoy, in some ways, this chapter because it makes me very reminiscent of working in a laser lab. It was something I really enjoyed. Okay, so if this is the first maxima at a non-zero angle, what is lambda? Okay, so we have sine theta is equal to lambda over d. And so lambda is equal to sine theta times d is equal to 2.3 times 10 to the minus 6 times sine of 54 degrees. Lambda is equal to 1.86 times 10 to the minus 6 meters, or 1,860 nanometers of light. Would you see this? No, it's non-visible. So typically when you're doing a problem involving light, I mean, it is fine to leave it like this, but you really should also put your answer in nanometers, because nanometers are what we use in terms of conventions. But you always want to be careful when you're doing these calculations to specify exactly what you're working in. So when I did, when I wrote my paper on the Rayleigh scattering length of light at different wavelengths, actually, as it travels through liquid and solid argon and xenon, I specified that this particular formula that I was using was in CGS units, so centimeters, grams, seconds. And so some papers will put things in nanometers, some papers will put things in meters, and you always need to specify with light exactly what conventions you're using. And it's good to restate it in terms of nanometers, just because that's what makes sense. It's kind of like we've talked about temperature scales, that, you know, really when we think about temperature from a physics perspective, it's always Kelvin. If you tell me a temperature of something in a lab and you use something other than Kelvin, I have no sense of what that means. I mean, sure, I could convert it, I could operate it mathematically, but so I'm just kind of letting you in on some inside baseball on typical conventions. So again, look for how things are specified, but when you do the calculations, I would always convert into meters, because I have seen things go wrong. And I've seen things go wrong in published papers where this has happened. So just do your calculations in SI units, where is natural, and then convert. That's just a good practice to get into. Okay, so moving on to S3.3, looking at angular resolution. So, and this is going to be the last section we cover prior to the final. I decided we do not need to do mechanical waves. There's some fairly, not too substantial differential equations in there, but enough that I think that it's fun. But it's the end of the semester, and I think you guys are either as tired as me or more tired, so we're not going to do that. All right, so in this section, we are going to get a little more practical. In our understanding of optics. So this is where my husband, who's a trained photographer, he would be all about this section. He's like, oh yeah, like, of course, camera lenses. Okay, so we want to know the impact of telescope mirrors or lenses on image resolution. So, by the way, we did actually do a version of this in the astronomy class. It's pared down quite a bit, but they did versions of these equations. Okay, so we want to know why two-slit interference that all maxima do not have the same brightness, which is true. And we want to know how the width of the diffraction grating determine the angular separation of maxima observed. Through the grating. And all of this is angular resolution. So delta theta is equal to lambda over W, where W is the width of the device. And more specifically, the illuminated portion. Okay, so that's what we're building towards, and now let's go after it. So we want to go after the width of the maxima. So the narrower the allowed width of allowed wave through a diffraction grating the easier it is to distinguish light of different wavelengths. Okay, so how do we go after this? Okay, let's define the width as the angular distance from the brightest spot to the darkest spot next to it. And so the dark area is adjacent to the minimum. Oh, sorry, the dark area is the adjacent minimum. Okay, so now we can go after width. Theta is the angle of the first maximum and the path difference for the slits is 1 lambda. So d sine theta equals lambda, and we're looking at a maximum. Okay, now we want the location of the adjacent minimum. We will call the adjacent minimum theta plus delta theta. And we want delta theta. Okay, so there will be a minimum of light if light passing through the first slit and the n/2 slit destructively interfere. So n is the total number of slits. Okay, and if you recall, the path difference between adjacent slits is 1 lambda, And so the path difference between these two slits is n over 2 lambda. All right, so this particular recorder is going to cut me off in just under a minute, so I'm going to stop this here and resume.